So this is a lab that I worked in called Council, the genetic testing. We built one of the big factory-style automated labs back in the day. This was a, I don't know, fluff piece by Wire where they're showing off all of the different toys that we were using. There we go, Council. As well as some of the people operating it. This was a, like I said, factory-style one where there was multiple arms going and handing off different things. We were processing about 1,000 samples a day, doing multiple assays on these to return people clinical tests. But this is generally what people are thinking of when you tell them automation. Actually, I should say that this is the automation for small assays and things like that, not like obvious large scale, the pipeline production things that seem to be fairly optimized for the automations that you're talking about, control features often. These are automation where you're building from the ground up for small scale or small assays with high throughput. So this is what people think about. This system probably cost about 20 or so million. I'm just going back to the game. Can you try to get to the next slide? All right, so that lab was a special case. That was it cost us about $20 million to build that lab. Also, it was the function of that factory style work was in order to the assays would directly lead to our bottom line. So the more assays we could put through there, the more money we were making off it. So it is a feed-forward loop, and that's why you can have companies like that can be successful with large-scale automation like that is very built for one express purpose. And you can spend a lot on the development and the maintaining of that system because of the fact that you're going to run it, and every time you run it, you're making money off of it. If you're not directly linking it to your bottom line, it's very difficult to build something like that and maintain it. Just the initial building and the development was most of that cost right there too. The maintaining it across many, many years when you're actually getting the return on investment is much less. It's a lot of cost at the beginning and goes lower at the end. But you have to make sure that you're getting something out of it to do that. Was that me? Okay. All right. So we're talking about artificial intelligence here and how automation is going to be able to assist and how you can best utilize it towards achieving your goals. So the bottom of the pyramid here, this sort of Maslow's pyramid of hierarchy of needs, but applied to AI. You get the data collection, and then you're going up to data infrastructure. This is the storage of your data. This is the tagging and giving it the metadata, such that you can go out back and retrieve it. You know where it is. You know the size and shape of it. You can make some sort of analysis on it in an automated fashion as well. So if you're doing well at this, you're doing a lot of data collection down at the bottom. It's high quality. It's going into your data infrastructure. And then data analytics and data science are in the classical world in terms of statistical analysis, usually combined together. This would be the regression graphs and things like that, whereas when you're going to use it towards AI, you're doing more of the labeling, tagging, and featurizing it. That's a word there. So you're tearing it apart, giving it all little values that you can go back to, and you can mix them up within your data science in order to give you sort of an evaluation there. And the AI is sort of sitting on top of all of these pieces and allowing you to get greater insight in looking at a wide swath of these data in different ways and combining them in new ways that you're not really seeing in an unbiased manner. And that's really an important part of this, that the computers have no real bias when they're looking at things. You can put in a lot of bias in different ways, which is a big pitfall in this, but really you're starting out with not much. Or with no bias whatsoever until you're starting to introduce it yourself. I don't know. So when you're thinking about data collection and whatnot, a lot of people jump immediately to lab automation. It's ultimately infinitely scalable, can be infinitely scalable, as well as in most people's minds, it then reduces the variability. You get perfect results every time, and you can ultimately scale it forever, right? So that's my entire talk. Thank you. We're back on time now, but that's definitely not the reality of the situation. So lab automation is a tool, just like AI is a tool. It's a tool that you can use to generate better data. You can generate more data, but you want to be able to make sure that you're making data towards the right goal. Like, these are all tools; they're not goals. And to separate the two is kind of important here. Almost every time I've been hired, I've been brought into a company that's got great ambitions and lots of money, and they're like, we want to automate everything because that's going to solve all of our problems. You've heard this before, Steve. That's going to solve all of our problems, and most of the time it just creates more and more expensive problems. So the idea is to get on some sort of plan and path that gets you towards that before you really spend a lot of that money and spend a lot of your time in wrong directions and really frustrating yourself and probably just putting an albatross around your lab's neck. So I'm going to give you the punchline first so we can think about it while I'm talking, and you can generate questions for later. Really, it comes down to what Bill Gates has said of applying automation to an inefficient process will just magnify the inefficiency of that process. And if you keep that sort of in mind, so you want to make sure that your process is really the most efficient process you can get. You want to make sure that the way that you're going about demonstrating that is a valid way of doing it and unbiased. You really want to just sort this out before you start in on spending a lot of money. A lot of people look at the automation, the robots that we're using, the $250,000 million robots, as very expensive. That's the cheap part if you do it wrong. So they will be even more expensive hires, they'll be even more expensive development at the time that you have it in your building and you're not producing data off it. These are all losses to your company. So really take it a step back and sort of think about what you need it to do. What you have today and how you can get it ready to be able to scale it up in the cheapest, most effective way possible. So let's start off with where I started, which was at UCSD at grad school, where the Legos came about. So we were in a lab. It was a learning and memory lab mainly, as well as molecular neurotransmission. And the first things that we were building were just things to was tapping the plates of the worms. So it was a very, very simple tool that you could program it, but I think it was every 25 seconds it would tap the plate, and what it was doing was stimulating the worms such that they would habituate to this, and how they were dealing with the taps and perturbance of their environment was what we were studying. This didn't need very, very, high tolerances, meaning it doesn't need to be very precise, as well as they're fairly simple tools and very cheap to build. In terms of the ROI, in terms of percentage of any project, which is return on investment, these were probably the best use case of my time in my entire career, as well as I took some of these and built a drug injection tool as well out of it. So I could take a picture on a microscope, and it would flash an LED bulb, which was controlled by the computer, and then the Lego would direct the drugs into the worms with the flash, telling you what time it did that. So those are some of the early ones. What you're seeing over here is actually somebody built a liquid handler out of Lego robots. These would be competitors to the Biomechs and Hamiltons out there. So you guys should be pretty worried about this, it looks like. It's just amazing that somebody did this. But in terms of buying or getting a robot, this might be all the tool that you need. If you can build it on a Lego platform, it's $300. It's very simple. It's very easy. You can have somebody maintaining your lab that's maybe a 12-year-old. Just get somebody's kid in there to make sure to keep it together. But yeah, And then the next one that I did in grad school, and neither of these were actual projects of mine. These are ancillary that were to try to help people in the lab move along, or help myself in the lab move along. They weren't really my projects. Worm Tracker, which was a very cheap microscope that built off a USB sort of microscope that you could then attach, and then it would travel around and follow a worm without disturbing it, while we did all sorts of horrible things to it, like pour drugs on it and ablate its neurons and whatnot. And this could characterize what was happening to that worm and what was happening within its brain with all those drugs and horrible things done to it. But that allowed us to create an array of about 12 to 20 of these microscopes, and one person could be operating on them, meaning we could collect a lot more data than one person alone following a worm around, plus that person would quit very, very quickly. After that, I went on to UCSF, and we were doing the canonical, what lab automation was really built for, which was screening of drugs back in the 80s. There was this idea that you just throw enough compounds at anything and we'll be able to figure out and pick out what the drugs are, and we'll be able to solve every single pathology out there, which clearly hasn't happened. And that's kind of the same thing that comes in with each one of these new, these new promises, like lab automation. Then the next promise was, well, I worked with the T cells after that, and they're going to cure all cancer, trust me. And then we've got AI. They're all tools. They're all waypoints. Nothing's going to be solving anything yet. I think that the AI in biology is going to be extremely interesting. It's got very powerful, can take a lot of different signals and marry them together. It's going to be a very big revolution once we can really figure out how to use it. It is still in its infancy. It's going to be a tough one. So this is the factory style automation called Council. Those are the robotics that I was working on specifically over there. And this was processing about 1,000, maybe 1,500 samples a day, 6 days a week, and it was running 24 hours a day. With the exception of Sundays, where it was sort of maintenance time. And this particular lab is actually considered one of the few success stories. There's not many labs that built any of this type of automation and actually got it they got it to successfully work often, but they couldn't get it to be successful within the company. And despite the fact that this company was pretty quickly sold off, it still is one of the ones, even 10 years on, that's still considered a success in Silicon Valley. Many companies will still reference these guys, reference what we did in their bids for venture capital. Here's another one. They haven't quite come out of it yet. They're still trying to get their clinical assay through, but there's a company called Freenome. Freenome is also building on top of a robotic platform, not only for the throughput and the scalability when they're actually going to be doing the clinical studies, but also because that they need the lower variability with the robotics. And what Freenome is doing is taking as many different analytes as they can get out of a blood draw, and then throwing them into machine learning algorithms in order to say whether or not the person has cancer. That's really hard. What's way easier with those models is to predict to tell us which machine those samples were run on, as well as which operators were using it. So these are very powerful algorithms. It's tough to detect early cancer, but being able to tell things like this is not something you want in your manufacturing facility. So for this, we went back into the lab in order to harden our protocols and make sure to get everything as I don't know, crisp is the right word, but make sure everything off the deck was as good as we could do, and everything on the deck was, was already automated. So there's small differences between the machines we couldn't stop, but when you're looking at the processes that people are running on the bench, that's where you can make a big difference. and you give somebody a protocol, and they can run it in 4 different ways. Most of the protocols and the way that we go and pass things back and forth between scientists is you're passing it off to somebody else who's had like a decade or so of experience as well. They know how to run things. They make assumptions already. Your formula or your instructions are maybe half a page long. You've got to take that out and be able to write something up in such detail and unambiguity such that you can hand this across to 6 different people, and this is done in manufacturing, where each one of them is going to run it the same way. If somebody doesn't spin a plate down at the right time, because you just assume no idiot wouldn't spin a plate down, or if it has bubbles and things like that, these are going to create problems. The biggest one that we had was the loading of our Illumina systems, or our Illumina sequencers, and this was, you would have a denaturing with sodium hydroxide, and each person was timing it in a little bit different way and getting things all together and loading it into the sequencer in a different way. So we went in, we rewrote the protocol, we gave everybody time buffers and gave people exact times to do it, and this was reduced by a significant margin, though we can still tell the difference between people. There we go. And the final place that I worked up until a couple of months ago was called Lyell Immunopharma, and this is the T-cell company that's going to cure cancer, along with the other 250 T-cell companies that are out there right now. So this is an earlier research R&D sort of function of these robotics. There was a lot of projects. They were smaller. We didn't have as much time for development on them. And oftentimes the goals would change throughout the project. That's really difficult for automation and any sort of hardware build, and when you're building out things like this, because you're going for a certain goal. If you change that goal in the middle of it, there's no guarantee that what you're building is going to accomplish that. But then also, it became fairly obvious that the larger projects, the ones that would change multiple times throughout it, were not really producing the ROI that we expected. Oftentimes these projects are taking 6 to 12 months, because that's just how long maybe these fully automated projects will take. And then they don't really start returning that investment for a year to 3 years. So the smaller projects were just helping people get by a single pain point was where we really saw a lot of traction. People were getting very quick adoption into the lab, and they were still doing all the same processes, these people that were getting the larger projects done, but they were doing it at 5 to 10% of the cost and being up and running and ready within a couple of months. Oops, let's go back. So, going back to the punchline again, because I've wandered off the path for a little while. Automation can help you create these large data sets with a scalable system, but remember, it's a tool, and you're trying to build towards that rather than, oh, I've got an assay, I'm going to go build the biggest thing possible to run that assay. And along the way, continue to confirm, am I on the right track? Test out your data. Make sure it's something that's giving you back something. And in the end, you will shrink the necessary data set in order to get better predictions or better conclusions out of it, and most of the rest of the things on that ladder are going to get cheaper and cheaper because you don't have to deal with such a big set. You don't have to run as many samples to get to the same conclusions. So confirm throughout the process what you're doing. And really, the other thing is focus on the operationalization of the assay rather than building the system and then trying to force the assay onto it, even though you might have misdesigned at the beginning. So operationalizing an assay is really being able to take it and put it into anybody's hands. You can do it by putting it on an automated platform, but you're still going to be doing the scripting out in an unambiguous fashion where you've got to tell it each exact step the whole way through. Or you could write that down for a human and train that human in an afternoon rather than over the course of 4 to 6 months. Additionally, one of the things that you really want to do is start thinking in the idea of success criteria. That's not typically how we're thinking as a research scientist, which is my background. You want to be able to say, yes, I need these amounts, or I need in between a range of X and Y for an extraction or something like that in order to proceed forward. Or if you're going to go for an assay, you want to get an answer out of it, then you might want to know the range that you're looking for that, and give yourself some very firm success criteria before you start up that development process, such that when you get to the end of the end of that experiment, you know how far off you are, or if you nailed it perfectly. If you nailed it perfectly, great, just move forward. But if you didn't get there, it might be better to go back into a development cycle than trying to push forward with what you've got. You're most likely got an assay that you're going to have to compensate for things elsewhere within the process, which may be difficult to impossible depending on how you put it together. How much would a failure cost? That's also a really important thing that you're going to need to know, because of the fact that if you can't fail, then your costs become much higher. If you can support some level of failure, if you can kick them out and you don't have silent failures and put them into the data set when they shouldn't be, you can probably get away with a lot of failures there, and that's not a bad thing. That actually makes it much easier to do it. So once you sort of considered all these things, then I would say start moving forward. And it's more of a planning phase than anything. Taking time to take a step back to have yourself go slow. Rather than go slow at the beginning to go fast at the end. This is something that I've seen happen to every single automation engineer and every single automation project thus far, which is you'll come in, somebody will say, we've got an assay, it works. Always define what works means. And then we're just going to put it onto a platform, and then we're just going to run that platform and do the development while it's on that platform. This does not work. It in fact makes your life even worse. If you'll see the little graphic over here, this is what you expect to happen in terms of automation, where you're working at this rate, you intend to put in a certain amount of development time and effort, and then as that takes over, you no longer have to worry about it because you've automated it. You can do it 1,000,000 times without actually having to put in much effort. And what happens if you aren't doing this and keeping track of all these things and just making it work on an automated platform, despite the fact that it might not be amenable to that platform, or you might have set it up poorly? It'll actually cost you a lot more time and money to keep that thing up and running than it would have just to hire an army of interns and have them do it over that summer. I would say that getting your assay up and operational before, maybe doping in some handy little instruments along the way is definitely a way to do it. And then once you get that system up and running, characterized and operational, transferring it to the automated platforms is much cheaper, much easier, much faster, and you don't have a bunch of expensive automation engineers standing around just wasting your money. So humans are incredibly useful in these. They have intuition. Oftentimes you can train them. And they come preloaded with a bunch of sensors, which is like your eyes, your hands, your brain. Like if a human encounters a problem with an assay or a workflow, they'll look at it. And most of them will come up with a conclusion that is generally in the realm of sanity, that they might be able to move it on, they might be able to write it down. If they see this multiple times, they'll be able to help you figure it out and get it up and running better. Whereas robots will completely shut down and do the weirdest thing possible. Especially in the lab automation realm, our error handling is not great. In fact, one of the first bots that we worked with, it's whenever it crashed like this, it would take everything, go to the highest place it could and release things. That was the error handling. And then spray everything else elsewhere, which came out with the blood spurting errors. That was a problem at council. If you want to talk about that, that's a pretty fun story. But the bots do not handle errors well. They will immediately shut down. You will get no information out of it. It's just done. humans capable of scaling up and down and work. They can work through imperfections. They have natural QC going on at all times. They will be thinking, hopefully thinking at all times. And they're extremely fast to train for new tasks. You can train a new team for a new task in hours to days. Whereas in terms of the robotics, they're much less flexible, and it will take you weeks to months probably. However, robots do things better. Certain things, like they don't complain. You give them repetitive tasks forever. They will not complain about it. They will not get tired. They will not lose focus. They do things like normalizations and hit picking, where you have to keep track of things and readjust things throughout it. Those are things that you can do on robots very quickly and easily. In fact, they've got the ML Prep by Hamilton over there, which is a great tool, very cheap tool to do these things, so you can keep them out of the hands of humans that will mess these things up. And they also have consistent timings. Consistent timings can be very helpful when you're developing these operational assays. You can have people have time clocks and things like that as well, but for robots, just do it automatically. Let's go. All right, so the idea is then to marry these two together, start out with the humans, operationalize the assay, move more and more towards instrumentation, and then build out your big platform. Once you have something, you know what you need it to do, you know it does do that, and then you can have it just turn the crank over and over and over again. You're starting out with flexible humans, you're moving towards an optimized robot. And optimized is in quotes there because optimized, it's a very squishy term in science. People say that they've optimized something, they've worked on it for a while, but they may or may not have optimized it towards the goal that you're trying to use it for. So really being able to check those things out before you're building something that is expensive. In the system area. You've got the cost, the capex of a giant system. You've got all the people around it that built it and are now maintaining it. And unless you're running it a lot of times to take advantage of the what you did make cheap, which is the per unit tests, you are actually probably losing money on this whole affair, and it might have been better to just stay with the humans the whole way. What I would say, have a plan for the next phase, have benchmarks, know when you need to hire those next people, know when you need to get that next system up and running, know when your bandwidth is going to be limited. That is what I'm trying to get together for people, is get those types of plans as well as execution of those plans. So we're back to the hierarchy of needs. Like I said, this is for data collection tools, and if you're getting high quality data, you might not need to crank that wheel so many times. You might be able to shrink this, which allows you to shrink the data infrastructure, which then might allow you to not even having to go up to AI. You might be able to get these off regression graphs that give you a lot of information as well. Let's go back. Yeah. So are there any questions?